Welcome to The Explainer. Today, we're doing something a bit different. We're putting together a serious institutional risk assessment on one of the most existential threats facing the entire digital asset space. We're talking about the quantum computing threat to Bitcoin. For most of its history, quantum computers breaking cryptography was just this distant, almost sci-fi worry. It was super easy to dismiss, but based on recent developments, that timeline is seriously compressed, and the race to fix it has officially begun.
We're using a bottom-line upfront approach today. We're going to compare sweeping network-wide migrations against more localized, agile solutions. We'll start by defining the quantum threat horizon, look at the defensive downgrade of protocol migration, and then evaluate Starkware's alternative QSB method. Finally, we'll cover future hash vulnerabilities and wrap up with a strategic risk outlook for your portfolio.
Okay, let's dive into this first section, the quantum threat horizon. We really need to define the vulnerability here. The immediate threat isn't actually to Bitcoin's mining process, it's to the transaction's signing mechanism. Specifically, the elliptic curve cryptography used to prove you own your coins. If a powerful enough quantum computer runs Shor's algorithm, it could literally derive a private key from an exposed public key in polynomial time.
To put the sheer scale of that threat into perspective, just focus on this number, 6.9 million. That is the estimated number of Bitcoin currently sitting in addresses that are wide open to a future quantum attack, simply because their public keys have already been exposed on-chain. And yes, this massive figure includes an estimated 1.7 million coins sitting in ancient addresses widely believed to belong to Bitcoin's creator, Satoshi Nakamoto.
When you look at the total supply exposure, it becomes immediately clear why institutions need to be paying attention right now. This exposed supply accounts for roughly 33%, a full third of all the Bitcoin in existence. We are talking about hundreds of billions of dollars at risk here. If a bad actor with a quantum machine reverse engineers those exposed keys, they can just seize those coins.
The real crisis, however, is a massive disconnect in timing. Look at the urgency versus implementation. McKinsey research suggests that cryptographically relevant quantum computers could emerge between 2027 and 2030. NIST is already mandating the deprecation of traditional cryptography by 2030. But on the flip side, Bitcoin's notoriously slow, consensus-driven governance model historically takes 10 to 15 years to implement contentious upgrades. The threat is just moving way faster than the network's traditional ability to adapt.
Moving on to Section 2, Protocol Migration. We're calling this the defensive downgrade. This is the first major mitigation path being proposed by developers, which involves a protocol-level post-quantum cryptography upgrade. We're talking about new address types in BIP 360 and a highly contentious migration of vulnerable coins proposed in BIP 361.
And this brilliantly illustrates the core engineering trade-off we're facing. Bitcoin's legacy ECDSA signatures are incredibly lightweight at just 72 bytes. But to make them quantum-resistant using NIST-approved algorithms like MLDSA, the signature balloons to over 2,000 bytes. And if we use hash-based schemes like Sphinx Plus, it jumps to nearly 29,000 bytes. We're talking about an absolute explosion in data size.
So what happens when you try to force those massive signatures onto a network with strictly limited block space? Well, according to a peer-reviewed paper in the JBBA, the impact is devastating. Their empirical analysis extrapolates that on permissionless networks, this transition will result in a 60 to 70% loss in throughput. Transaction fees would skyrocket, and the network would basically grind to a crawl.
But honestly, the slow transactions aren't even the permanent problem here. These massive signatures create what researchers call state bloat. We are looking at a 59 times permanent storage increase per output. If fully migrated, the Bitcoin UTXO set would blow up from 5 gigabytes to nearly 300 gigabytes. Every future node would have to store this extra baggage forever, which severely accelerates centralization risks.
To summarize this whole path, that JBA paper frames the protocol migration perfectly. It is a defensive downgrade. Unlike past upgrades that gave users tangible benefits, this post-quantum migration imposes immediate, severe costs. Capacity loss, massive state bloat, and a likely decade of brutal governance battles over whether to permanently freeze Satoshi's unmigrated coins, all of that pain just to maintain the status quo of security.
Section 3. Alternative mitigation. Thankfully, a heavy network-wide mandate is not the only option on the table. Let's shift gears and evaluate the primary alternative that's making waves right now. Avi Levy's Starkware Quantum Secure Bitcoin Transactions, or QSB.
Starkware's QSSB provides an incredibly elegant, localized shield.
The mechanics here are fascinating. It achieves 118-bit pre-image resistance, which is robust enough to thwart Shor's algorithm by cleverly using existing transaction lookups that are already built into Bitcoin script. The absolute game changer here is that it requires no soft fork and no hard fork. It's fully backward compatible. When we objectively compare these two directly, the contrast is kind of mind-blowing. Protocol-level PQC mandates a heavy, network-wide migration through a contentious fork, forcing that massive throughput loss on everyone. Conversely, Starkware's QSB acts as an agile opt-in layer. It trades off a messy protocol overhaul to instead secure individual transactions locally. Users and institutions can organically adopt it at their own pace, much like how we saw the gradual, successful adoption of Taproot.
Let's move to and see how this builds into Section 4, Hash Security and Future Vulnerability. We've talked a lot about elliptic curve signatures, but what about the long-term viability of the hashing functions themselves, the stuff that actually secures Bitcoin's mining?
While Shor's algorithm breaks signatures, Grover's algorithm attacks hashes in symmetric cryptography. By applying quantum search, Grover's algorithm mathematically halves the effective security margin of a hash, meaning under a quantum threat, AS256 essentially drops down to the security level of AS128. It's technically still secure for now, but it's forcing the broader cybersecurity industry to start migrating towards SHA-512 standards just to stay ahead of the curve.
And we are already seeing theoretical cracks forming. Cutting-edge cryptographic research shows that by converting semi-freestar collisions into two-block collisions using quantum machines, researchers can successfully attack 38 out of the 64 steps in reduced SHA-256. They are proving this works faster than generic attacks using a time-space trade-off metric. It tells us that even hash-based security might face real algorithmic vulnerabilities as quantum techniques continue to improve.
Finally, Section 5, Strategic Risk Outlook. How do we actually synthesize all these competing mitigation paths into a coherent forecast for institutional portfolios?
So the crucial point is that institutions must demand a clear, agile playbook right now. You have to monitor those quantum qubit thresholds closely. You need to demand that your custodians build out quantum-secure tooling like QSB support early. Portfolios must prepare for a fragmented ecosystem with split security tiers. Think grandfathered classical accounts versus new quantum-secured accounts. And finally, analysts must seriously reevaluate the governance risks associated with proposals that might forcefully freeze legacy coins.
I want to leave you with this final provocative thought. How will financial markets actually price in the quantum discount? Knowing that Bitcoin must eventually pay a steep scalability price, a defensive downgrade, just to survive, how does that impact your long-term valuation models? It's a massive engineering hurdle, and the clock is officially ticking. Thanks for joining me on this explainer. I hope this deep dive gave you the clarity you need to navigate the quantum horizon.